In physics, it's often useful to know how things are going to behave during a collision. The topic of momentum is very useful for this. Now, there's two types of momentum. One's called angular momentum, and you don't need to know about it on this course. It won't come up even in A level. But that's kind of the momentum something has because it's rotating. The one we are going to look at in a lot of detail is linear momentum. And you would have touched on this at GCSE. It has the symbol small p. And the way you calculate it is you do the mass times the velocity of the object. Velocity, it's important to say velocity, not speed, because direction is important in momentum, and that kind of makes sense in collisions. In symbols, little p equals mv. Units of mass, kilograms, and velocity, meters per second. So that gives units for momentum of kilograms, meters per second, like that. Don't write kilogram meters per second. No, not correct. You'll also notice that velocity is a vector. Well, you won't notice, you should know that, which means that momentum is also a vector. Direction is important. Now, one principle that you will have also touched on at GCSE is the conservation of momentum, and that is really important when we solve these problems. What does that mean? Conservation of momentum. Well, you've heard of other laws, conservation of energy, conservation of charge. So you probably have a rough idea of what this means. For any closed system, okay, now a closed system means basically that there's nothing else going on externally. So, for example, when you watch yourself maybe coming to a stop as you're running, it looks like your momentum has just disappeared because you were moving and then you stopped moving and it's not been passed on to anything. But that's not a closed system. You have to conclude the Earth in that to complete the closed system, and the Earth does actually move when you stop. Your momentum is conserved and it's kind of passed on to the Earth. So, for a closed system, the total momentum of all the objects before the collision or whatever it is, for whatever's happening, is equal to the total momentum of objects after the collision, i.e. the momentum is conserved. And that's an important rule that you need to know and be able to quote, and we will use it when we do questions. Let's have a look at this question here, which is kind of a typical GCSE question using that conservation of momentum. You've got the situation where there's a girl catching a ball on an ice rink, a classic thing to do on a weekend, and we've got a situation before and after. So you've got to remember that the total momentum before, so total P before, is going to equal the total P, which is momentum, after. Before, we have a ball moving, so we have the momentum of the ball, and we have the momentum of the girl, which we'll see what that is in a minute. Afterwards, likewise, we have the momentum of the ball, the momentum of the girl, although they're both now together, so we'll consider that, what that means in a minute. Right, start off with the momentum of the ball before, so this side of the dotted line is all before. So before we have m times v, and for the girl, likewise, we have m times v. However, the v is going to be 0 for the girl, because she's not moving, so 0 times 60 is obviously going to be 0. And for the ball, we have 15 times 20. Now, the units are kilometres per hour. It's a bit of a pain, but if we leave it in that, our answer will just come out in kilometres per hour. So we'll leave that like that. Normally, we'll get meters per second, though. So 15 times 20 gives you 300, plus the 0, which is we just ignore. So that's the momentum we have before. And that's got to be conserved. So it's got to equal the momentum afterwards. In this case, the two objects have stuck together. So there's now only one object here. Just consider her and the ball as one object. And her total mass is just the sum of the two. 60 plus 15 gives you 75 kilograms. So it's a bit easier afterwards. We've just got the mass times the velocity of this whole object of the ball and the girl. So 75 times v, because we want to find v. So now we're left with this equation here, which is nice and easy to solve. If you do 300 divided by 75, I'm sure you can do that in your head. You're going to get 4 as your answer. And remember, the units will be the same as earlier, which is kilometres per hour. A bit of a pain, those units, but still useful to know. That kind of makes sense as well, because the ball's moving quite fast, but it's not as heavy as the girl. So she's going to move off at a slower speed than that ball was moving, because it's kind of getting her moving as well. Let's now consider another type of, well, it's not really a collision. This is called more of an explosion. At the start, before, we've got myself on a boat holding a ball, which is 10 kilograms. The mass of me in the boat is 100 kilograms. Just made the numbers nice and easy. Afterwards, here I am again in my boat, and I've thrown this ball off at 20 meters per second. I'm trying to get to this island over here. So, I mean, just looking at this, you can probably guess what's going to happen. I'm going to move this way. We want to know what speed I move at. So what is V for me in the boat afterwards? Now, remember again that momentum before equals momentum afterwards. That hasn't changed. That will always apply. But it's different in this case because actually the momentum before, everything is still. Nothing's moving. I'm stood in the boat with the ball in my hand. So the momentum before is actually just zero because I have no velocity and the ball has no velocity. Afterwards, we need to think about what's going on. And because we've got things going in opposite directions and velocity is a vector, and so is momentum, we need to define a direction. I'm going to say right is positive and left is negative. You're cool. As long as you're good with your maths, you will always get the right answer. So we have two things. We have me, so the momentum of me plus boat, and the momentum of the ball. And that has to sum to give zero. Momentum of me is my mass times my velocity, and then the momentum of the ball is the same there. Put my numbers in, my mass is 100, and it's times V, which we want to find out. And that's added on to the momentum of the ball, which is 20 times 10. If we simplify that, we get 100V plus 200 equals 0. And we want to take the 200 over the other side, so it's negative 200 equals 100V. Now we need to get rid of the 100, they're times together, so we divide, and we're left with V is equal to negative 2 meters per second. What does the negative tell me? Well, that's good news, because if we look back up here, we said negative was to the left, so we know that I'm going to move to the left, which is what normally happens in an explosion. Other good examples are recoil in a gun, or if you throw anything in that direction, you feel a bit of recoil in the opposite direction. In fact, if you fired a gun on an ice rink, you'd move backwards as the bullets move forwards. Obviously, you don't move as fast as the bullet because you're not the same mass as the bullet, otherwise you would there. Other good examples of fireworks, because if you think just before a firework explodes, that's a firework represented there, it's stationary. Imagine it stops for a moment in the air just before it explodes. It's got no momentum. But then everything comes flying out in all directions. Momentum has to be conserved. So actually, when you add up all the momentum of those little bits coming out, all those bright little lights, they've got to sum to zero. And that's why it explodes out in all directions. If it exploded in one direction, momentum wouldn't be conserved unless something goes in the opposite direction. During a collision, there's two types that we can consider, elastic or inelastic. In an elastic collision, imagine we had this object hitting this object. This one's going to have some kinetic energy before the collision. If all of that energy is conserved, well, I mean, energy will always be conserved, but if it's all conserved as kinetic energy, then we call that an elastic collision. If it's not all conserved, so say that collides with that, but some of it's lost as sound, heat, which is basically what happens all the time, then this is called inelastic. So kinetic energy conserved, elastic, K not conserved is inelastic. Okay, and this is where it's transferred to other types, to other forms. Kinetic energy is conserved. Now, is the energy conserved in both these? Well, yes, energy is always conserved. So when we look at all the energy, it will all be conserved. It's just the kinetic energy which we're talking about in here. Momentum is also always conserved, as discussed previously. So it doesn't matter which type of collision it is, momentum is always conserved. The only difference is whether kinetic energy is conserved or not. Let's now consider this slightly odd example. A rock is above the earth and it's about to be released. As it's released, obviously its weight will pull it in towards the earth and it's going to speed up. As it speeds up, it's gaining velocity. If it's gaining velocity, that means it's going to be gaining momentum. And then we seem to think, well, where's this momentum coming from? This rock had no momentum before. So before, the rock's momentum, the total momentum was 0. After, the rock now has momentum. Well, that seems to break the law of conservation of momentum. It tells us that something must be moving in the opposite direction to the rock to make the total momentum zero. Well, actually, funny enough, it's this thing over here, this big lump of rock called the Earth. The Earth is going to actually move towards that rock as that rock moves towards it. In fact, we can do some calculations just to see how fast it does move. Why don't you have a go at that pause the video once you've got enough information and have a go at it yourself. So the momentum before must equal the momentum after, as always. And the momentum before, we know at least that rock was zero. The Earth and the rock were still. No velocity, no momentum. Afterwards, the rock's going to have momentum and the Earth is going to have momentum. We might want to define some directions here. Let's say the direction the rock's moving in is positive, the opposite direction is negative. If we then say that the rock was, let's say, 100 kilograms, and we'll say it's moving at, to make the numbers nice and easy, 100 meters per second. The mass of the Earth is 6 times 10 to the 24 kilograms. And you can now have a go perhaps at working out, pause the video and have a go at working out how fast the Earth must move and in what direction. Remember, if you get a negative answer, we know it's moving upwards. If you get a positive answer, it's moving downwards, but that will be a bit weird. I'm going to now do that over here. So the mass of the rock was 100 times by its velocity, which was a positive 100. And that's plus the mass of the Earth, 6 times 10 to the 24, times the velocity. Probably spotting something, well, the mass is so big, that's probably going to mean that the velocity is quite small. 100 times 100 is 10,000. And I move that over to the other side by subtracting it. So 100 times 100 is 10,000, then subtract that over to the left-hand side over here. That leaves us 6 times 10 to the 24 times v on this side. So to find v, we need to divide negative 10,000 by 6 times 10 to the 24. We're going to need a calculator for this one. You should get negative 1.67 times 10 to the minus 21 meters per second. Probably too many sig figs there, but oh well. Quite slow as you can see, but it does actually move by that amount. If you want to actually check, see how much that is compared to the size of an atom, you'll see that is pretty small, less than the size of the atom the Earth moves, so we can't really measure it. But it shows that actually momentum is conserved. And if the Earth had a smaller mass, then you would see that velocity moving. Let's consider this situation now, which could be very similar to if these were snooker balls. But I'm going to imagine we've got two cars, a red car here, shown here, and then a blue car shown over here. The red car is driving along, hits the back of the blue car, and you can see that the blue car is not to the right afterwards, so it must not hit exactly on the back, maybe over this side somewhere, goes in there, and the red moves to the left. Now, momentum is always conserved, and so far we've done it in kind of one dimension. Now, though, we're going to consider it in 2 dimensions, x and a y direction, because things often move like that, unfortunately. And that adds a kind of layer of complexity and will require you to think about the components given these are vectors. So let's consider before. The only thing that has momentum before is this. So let's draw a vector arrow for that. We'll just say that's the momentum of the red. I'm going to do it in red. I'm going to call it before. Afterwards, the red car has momentum in that way. We don't know how big, but I'm just going to show you something here. And that's the momentum afterwards. And the blue one has some momentum. Again, we don't know which one's going to be bigger, which one's going to be smaller in that direction. Well, given momentum is always conserved, we can turn this into a vector triangle, and this should be a closed vector triangle given that the momentum is conserved. So whatever momentum we had before is going to equal the momentum afterwards. So if we draw the momentum before like that, and then we draw, so this is P before, and then we take our 2 arrows from here, draw them top to tail, again starting from the same, it should equal that vector there. I'm going to do it, I'll just do it in red again. Momentum afterwards, something like that. And if this was all drawn to scale correctly, it would end up with a nice closed triangle like this. And this is the after ones on the left, and the momentum before on the right. The idea being that momentum is conserved. This momentum here is equal to this momentum afterwards. So you could always do vector diagrams to solve these problems. And if you do them to scale, just like we did in our last topic with forces, you will get a good answer. Let's consider this question here. Pause the video and have a read of it. So we have these two balls or particles coming together. First of all, I'm going to convert their masses into kilograms because that's the SI unit. I just like kilograms. There we are. They also stick together, so we know the mass of this object is going to be those two added together, so 0.07 kilograms. Now, as you probably guessed from the forces, we're going to have to deal with this by splitting it up into components. I'm going to start with the horizontal, so in that direction, component. Ball A is the only one with a horizontal component. B has no horizontal component. And it's nice and easy in this case because they only have horizontal and vertical. They're not going off at an angle, but you could have to deal with that. So in the horizontal direction, we've got 0.04 times 35 as the momentum before. And that's going to be equal to the momentum after. And ball B does not contribute any momentum in that direction. Afterwards, they both have combined together, so their total mass is 0.07, and that has a velocity in the, say, in the horizontal direction, like that. If you solve that equation, you'll get VH, and you can do that yourself, is it approximately equals to 20 meters per second. That's in the horizontal direction. That's the horizontal component of the velocity. Let's now take the vertical direction. Again, momentum before, and always write this so the examiner knows what you're talking about, equals the momentum afterwards. Before the ball is 0.03, or the particle, and it's going at 35 meters per second as well. And again, that's going to be equal to 0.07 times by the velocity in the component of the velocity in the vertical direction. Give it whatever symbol you want. If you solve that, you'll get 15 meters per second, and that's in the vertical direction. And as we know, so good this, we did this with forces, we've got to find the resultant, we can draw a quick vector diagram, that's 20, that's 15, and the resultant is going to be that there. And this is right angles. So, thinking, Pythagoras, that's going to give me the value here. So the final velocity, which is what we're interested in, is squared, is equal to 20 squared plus 15 squared. If you solve that equation, you'll get an answer 25 meters per second as the speed of those two particles afterwards. This is a slightly more tricky question, so please do pause it and read over that. So we're going to solve this in a very similar approach to last time, but it's a bit trickier this time because we've got angles going on. So they're not exactly right angles, as you can see there. Let's start by considering the horizontal motion again. And remembering that momentum before equals momentum afterwards, P being momentum. And we know that this robot over here has momentum because it's moving, but this little crabby thing doesn't there. If I were you, I'd take the things from the question and write them on. So we know that robot A has a mass of 20 kilograms. And the speed is already there. And the robot B has a mass of 12 kilograms. That makes it useful. Calculate the magnitude and direction of the velocity of robot B. So we need to know the magnitude and the direction. So we need to know V and beta, because that's going to be the direction, the angle. So before, this robot here is not moving. So U of this robot is 0. So momentum before just consists of the robot A. It's easier to label them up, which is 20 times 2. If we add on robot B, well, that's just going to be 0 times 12, so it's 0, but I'll write it there for completeness. And now we need to consider the components of robot A and B. For robot A, you can see the component in the horizontal direction is going to be 1 cosine 30. One is the velocity. Cosine 30 is to work out the component of that velocity. I'm going to draw it on that component there. If we complete that up, it's made up of two components. We're interested in this component here, the horizontal component. If we then solve this, and then plus, obviously, I forgot that we're going to, of course, have the component of robot B, and we're just going to call that the, how do we want to do this? Let's call it the M times the velocity of B in the horizontal direction. Now the good news is we know m, because that's the mass of robot B, we know that's 12, so it's 12 times VB, and 1 cosine 30 will give you about, I've made a little mistake here, so I haven't included the mass, c times 20, this is momentum, so it's mass times velocity, so 20 times 1 cosine 30 will give you about 17.3. Solve that equation, and you'll get the velocity in the horizontal direction for robot B of approximately 1.89 meters per second to the minus 1. Sorry, that's a bit messy. I'll make sure this one's a bit clearer. We're going to now repeat in the vertical direction, so if that didn't make sense, hopefully this will now. In the vertical direction, it's a bit easier, because actually before, robots A and B do not have any component in the vertical direction. So the momentum before, which consists of the momentum of A plus the momentum of B, that's going to equal the momentum afterwards, which again is the momentum of A plus the momentum of B. But these two are 0 before. However, for the other two, they are not 0. And we have to find directions here. We'll say up is positive, down is negative. So robot A, its mass, again, is still 20. And that's going to be times by 1 sine 30, because that is this component going up here. Right angles there. Plus, again, the mass of robot B times by its velocity, its component of its velocity anyway, in the vertical direction. I'm just going to call that VV. I'm sure there's a better symbol for it. Now, if we solve this, 20 times 1 sine 30 is going to give you 10. Sine 30 is a half. So 0 equals 10 plus 12 VV. And then take the 10 over the other side is equal to that. And then VV is going to be minus 10 divided by 12, which is negative 0.83. Now to find the actual velocity, because remember we've actually now just got over here, we've got one component, and over here we've got the other component. Just like earlier, we can turn those two into a vector diagram if it helps visualize it. In the horizontal, we've got 1.89. In the vertical, we've got negative, so downwards, 0.83. And the resultant is this one here. So we see we can use Pythagoras again to find that velocity. Like that. Solve that equation, and you will get approximately 2.1 meters per second to the minus 1. How do you find the angle? Well, you're probably guessing it from looking at this. We can use trigonometry. There's the angle, and this is right angles. If we label these up, if we label these up, we've got the opposite over here, the hypotenuse here, and the adjacent. So that means we can use tan. Tan of the angle is equal to the opposite over the adjacent. The opposite is 0.83, adjacent is 1.89, and if we solve that by doing the inverse of tan, theta will be equal to the inverse of tan of that calculation, you will get approximately 24 degrees. So we've got our two answers there. Oh, that was fun. We know the velocity, and we know the direction there, which answers both of those.